Hi, Dr. Caps. Welcome to my lab. This one's probably going to be a bit choppy just because of the nature of having to get so many balloon models ready to go. But I am sitting here with my balloons and we shall get started. So we'll start with the one with the number of electron pairs with 2 in it. I'm not entirely certain how to model this, if I'm being completely honest, so I figured I'd do something sort of like yay, which don't pay attention to the size of the balloons, but the middle atom, which is E in all of the models, would be in the middle, and then each element or electron pair or whatever would be one of each balloon. So we'll start by modeling this linear one. So you have 3 elements in it. You have this guy, the middle one, and this guy. They are linear because they repel on each other in an equal amount. And there's no electron pairs to sort of bend them one way or another. There are 2 bonds, one single bond here and one single bond here. It could be more than just a single bond, but in this demonstration it is a single. There's 180 degrees between each bond. A specific molecule that might represent this is SO2. There isn't a different electron domain geometry because there are no other electrons sort of in this situation. And the molecular geometry is linear. All right. Moving on to a model where the number of electrons pairs is 3, we have this sort of situation going on. So this is a trigonal planar molecule. So there is the central atom followed by 3 atoms sort of pushing on each other in an equal fashion. This blue one up here could be another molecule or another element, or it could be a lone pair of electrons. So the electron domain geometry of this guy is trigonal planar, but the molecular geometry, depending on whether this is an element or whether it is a lone pair, is either trigonal planar for an element or bent for an electron pair. An electron or a molecule that would be bent would be H2O, water, and a trigonal planar one would probably be something like HO3 or H3O. Sorry. All right, these are going to be increasingly difficult to hold together, so I'm not entirely certain what the plan was, but we're just going to keep trying our best here. So this is our tetrahedral model. So there is a central atom and then 3 sort of around the bottom and 1 on the top. And obviously this is just how I'm choosing to arrange it. It could be in any sort of direction. There is a 109 degree angle between all sort of molecules here, or elements. I keep calling them molecules, apologies. All elements. So this is tetrahedral, assuming that these are all elements. If this top one here were just a lone pair, it would be trigonal pyramidal. And then if 2 of these were electron pairs, this guy and this guy, this would actually have a molecular geometry of bent, because the electrons are sort of just over here, not contributing to molecular geometry. A molecule that might have a tetrahedral shape, sort of like this, tetrahedral molecular geometry, would be something like methane, or not methane, CH4. I think that might be methane. I think it's methane. All right, we're back with our number of bonding sites being 5 for a trigonal bipyramidal. This is a little off. It should be a little bit, these 2 green ones should be a little bit farther down. And then you would have 90 degrees between all 3 of these. And then about 120 degrees between these green ones, but I do have to have my hand here, so can't really get it to do that. So a trigonal bipyramidal type molecule has the central atom and then 5 different atoms around it. If one of these happened to be a lone pair, it would be considered a molecular geometry of a sawhorse or a seesaw. If 2 were, it'd be T-shaped, and then if 3 were, it would be linear. It would be these 2 with these 3 sort of, these 2, this guy and this guy, with these 3 sort of contributing to the overall shape of the molecule. Sorry, I forgot to include a molecule that might have this trigonal bipyramidal molecular geometry, and that would be phosphorus pentachloride, where the central atom here would be phosphorus, and then you would have 5 chlorine atoms attached to it. All right, last but not least, we have a molecular geometry of octahedral. I can't quite keep it together, but every molecule sort of has a 90 degrees between all of it. There are 6 bonds, so there's a central atom in the middle, and then all these atoms should have about a 90-degree angle between them. Assuming that these are all atoms, this would be octahedral for its molecular geometry. You add in 1 lone pair, you get square pyramidal. 2 lone pairs, you get square planar, where these 2 would be your lone pairs, and then everything else would make it a square. 3, you'd get T-shaped. Ooh, dropping balloons here. And then 4, you would have linear, where this orange and the purple one would be your atoms, and everything else attached would be your lone pairs. An example of a molecule that would have this would be sulfur hexafluoride, where it has more than you would expect a molecule to have for bonds, but because it is in like the 3rd or 4th row of the periodic table, it is able to do that by utilizing its d orbitals. And that is all for my presentation today. My hand is cramping from holding the balloons together for so long. But thank you for watching, and I hope you have a good week, Dr. Caps.